Okay, so if we're kind of switching gears from ionic compounds back to molecular compounds, one of the things we said about molecular compounds is that they contain only covalent bonds. And we said a covalent bond is electron, actually two electrons, or electrons shared. Okay. Yeah. Covalent bonds formed by the electrons are being shared. All right. I kind of feel like some of these are review slides. Like it's like we already did a slide like that, and you're right. Okay. Molecular or covalent compounds have only covalent bonds. And then we said ionic compounds contain at least one chemical bond. That's an ionic chemical bond. One ionic bond. And we said ionic bonds, electrons are not shared, they are transferred. Yeah, kind of like that. Doesn't this seem like we already did this slide? You're like, yes. So back in the previous unit, we talked about the periodic table. We said the JAG separates the metals from the nonmetals. And we said that if it has a metal in the formula, then it's an ionic compound. No metal, and it is a covalent compound. And your homework that you handed in is one of those things that you did. Okay. And we talked about this before, the homework that I handed back to you guys. You guys did those electronegativity values, the chi values, and you said that you can look at two atoms that you know are going to be bonded together, and you can see if electrons are going to be transferred. If the difference in their electronegativities is more than 1.7, then the tug of war is lost. The one with the higher electronegativity, which is the nonmetal, will just basically get the electron or electrons. Okay. So as we're switching gears to molecular or covalent compounds, kind of for now anyway, we are only dealing with nonmetals. So do you kind of recognize the JAG here? The JAG kind of that, yeah. This is my JAG. Okay, separating metals from nonmetals. So these nonmetals, if you pick a pair of them, to stick together, their electronegativity difference is going to be less than 1.7, so electrons are going to be shared when you stick those two together. Notice that for you people you biologists, life on Earth anyway is carbon-based life. And so a lot of life actually has carbon, hydrogen, oxygen, nitrogen, okay? So a lot of this stuff is what makes what we call biomolecules. So we have a lot of covalent bonding going on. So those lines show you electronegativity. Electronegativity increases across the period and as you go up the group. That's kind of what that's showing you. I usually like to take, one of these days I should move my arrow, but I usually like to take this arrow and put it over there. It's the same difference. And in your homework that you handed in that I just graded this morning, you guys arranged elements in order of, was it increasing electronegativity? Remember, this is the pull that an atom has for electrons when it's connected to another atom. Okay, we're just kind of zooming along here. I want to show you kind of a simple Lewis structure of water. So you guys would tell me that the formula for water is H2O. And so H2O, I'm going to kind of do it this way. Because if you're going to draw the Lewis structure of anything, and we'll be talking more about this a little bit today, a little bit Wednesday, and in the lab on Thursday. If you want to draw a Lewis structure or anything, you have to kind of come up with what I call the pot of valence electrons. So here we go. We have two hydrogens. And how many valence electrons does a hydrogen bring? Somebody say 1, 2. If you look at hydrogen, it's only got 1 proton, so if it's neutral, it has 1 electron. So 1 valence electron. Okay, so 2 times 1 is 2 electrons. How about oxygen? There's 1 oxygen atom in water, and I'll remind you how this works. If you find the element on the periodic table, whatever its group number is, that's how many valence electrons it has. So look at your periodic table and find oxygen. And then the group number is how many electrons?
6.
It is 6. You didn't look at a periodic table.
Yeah, I did.
Okay. So it's a 6A, so 6 valence electrons. Perfect. So I'm liking that. Okay, so 2 plus 6 is 8. Now this is actually, I'm going to call it the pot of valence electrons that is in an H2O molecule. We'll talk about how we get to this point, but here we go. Here is the Lewis structure for water. So it has, not so surprising, and I think we looked at it before, not so surprising, the oxygen is the middle of the 2 hydrogens. So we have oxygen bonded to a hydrogen and oxygen bonded to the other hydrogen. It would feel weird to put an oxygen on the end, I think. So I'm going to finish this thought, but I think, did I mention this before? Anytime you see a dash like that, that means a covalent bond. And covalent bonds, each covalent bond has 2 electrons. So right now I have 2 plus 2, I have 4 electrons being shown there. And then what I'll kind of drill into you is that if I have 2, 4, if I have 4 electrons shown, my pot of 8, well, I got to do something with another 4. And the way it works is they're called lone pair electrons. And the word pair means they come in pairs. The word lone means that they're kind of hanging out there. So here we go. 1, 2. We have what I call 2 pairs of lone pair electrons. Okay, dot, dot. I call them dot, dots. Dot, 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 dot. Lone pair electrons. And a few things about those lone pair electrons. They feel kind of invisible because there's no atom connected to them. But a cool thing about the lone pair electrons is actually they add shape to the molecule. They are actually what bends those 2 hydrogens down. That's why water is not what we say linear. So bottom line is if we count electrons now, I'm like in 2, 4, now we have 6, 8, and one of my things is, not just my thing, but what's on your Lewis structure should match up to what your pot is. So we have 8 electrons in our pot, 8 electrons on our structure. The reason I want to do this for this slide, kind of bump it up a little bit, is do you see where every time you see a dash on a Lewis structure you've drawn or a Lewis structure interpreting, think of 2 electrons. And I just think that is so cool. Those pair of electrons they have joint custody by the oxygen and by the hydrogen. Okay? That's the double dipping. All right, very good. Okay. So you guys have your Lewis structure of water in front of you. And if you were to count electrons around the oxygen, the electrons around the oxygen actually are 8. And most atoms want 8 electrons, with an exception on the final Lewis structure, with an exception on boron, which just wants 6. So here's my water molecule again. Dot, 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 dot. So it's kind of like a Venn diagram sort of thing. If I draw a circle around it, okay, I count 2, 4, 6, 8. Now, if I draw a circle around my hydrogen, it's only got 2. But honestly, hydrogen is happy with 2. Because what rare gas, what group 8A element has 2 electrons? It is like helium. Very good. It's got 3 eyes right there. So 2, and then the other one is 8. So we talk about the octet rule, and that's kind of where they're sharing electrons, making sure all atoms in the molecule are happy. Boron will only want 6, and we're not going to do really anything like this semester. If anything greater than, let's see, period 3, which is a lot, beginning at period 3. So basically find period 3, and that's like sodium, magnesium. So basically all those stuff down there, sometimes they can have what's called an expanded valence, and they will have more than 8 around them. Oxygen has 8, we're going to go with 8, or 2 if it's hydrogen, or 6 if it's boron. Okay. So we talked about, I know this class builds on itself a lot. Remember we talked about finding homes for electrons, and we found homes for electrons in orbitals, little boxes. Those are orbitals of the atoms. Those are called atomic orbitals. Well, the deal is if an atom A wants to join with atom B, I think I'll do it this way this semester. Here's my atom A, and it wants to join with atom B, and I'll kind of make where I have the letters for them kind of their nucleus, okay? And my favorite way to kind of show this is to pick a, what kind of orbital has this shape? Do you remember? Dumbbell shape. It is a P, very good. So that is one of A's atomic orbitals. I'm going to go over here. I better pick maybe a different color. And this is one of B's atomic orbitals. P orbitals, very good. And do you see where I showed them overlapping right here? So the red and the purple are the atomic orbitals of the atoms themselves. If they're going to join together, they make a new orbital. It's a bond orbital. So let's pick green. This right here is the bond orbital. A bond, and it's the bond orbital is formed from the orbitals of each of the 2 atoms. Okay, I think that's so cool. But each box, you would tell me a normal atomic orbital can only hold 2 electrons. So also a bond orbital holds 2 electrons. So bond orbital will have 2 electrons, and it's also similar to orbitals of the atoms, atomic orbitals, because you told me if you put 2 electrons in one orbital, you have to show one up and one down. What does that mean? One arrow going up and one arrow going down. It's opposite.
It's like electron.
No, it starts with the letter S. Yeah, box and arrow diagram. That's what I'm talking about here. You put 2 electrons in one orbital.
Spins.
Opposite spins, exactly. Yep. And then this is probably, I don't know if this is the coolest thing of them all, but remember when we did water a minute ago, we said the hydrogen brings 2 electrons to the pot and the oxygen brings 6, and we just kind of distributed them over the water molecule. It doesn't matter when you put a pair of electrons that are going to be shared to make that that covalent bond. It doesn't matter if those electrons both come from one atom, okay, or if those electrons come from one and then the other. It doesn't matter. It's so fun. So the final Lewis structure, I'm going to draw some final Lewis structures for you, and we'll be able to do these later on. But I'm going to draw a carbon, single bond carbon. This is actually going to be C2H6. And then here we go. Let's just put some hydrogens. Let's put 3 hydrogens on each carbon. Not the prettiest structure I've ever drawn, but that's okay. C2H6. So anytime you see a dash, it's like I've been saying, think of 2 electrons, okay, that are connecting those 2 atoms. All right. Well, sometimes we actually have what's called double bonds, and we do 2 dashes, and guess how many electrons there are? Not just 2, 4 electrons, yep. So now this is going to be C2H4. And it looks like this. So each carbon now only has room for 2 hydrogens, not 3 hydrogens. So this right here, the double dash, is a double bond. And it has 2 pairs of electrons. And 2 pairs means 4. Cool. And then last but not least, and I think I'll put it right here next to my C2H4, is C2H2, where we have a carbon, 3 solid dashes next to the other carbon. And now it only has room or can accommodate 1 hydrogen. So 1 hydrogen on the left and 1 hydrogen on the right. Very symmetrical, aren't they? So that is obviously a triple bond right there. So how many electrons are there in a triple bond if each dash is 2 electrons? 6, exactly. Yep. There are 3 covalent bonds. Each covalent bond is 2 electrons, so there are 6 electrons there. Perfect. Now, before we move on, let's go ahead and pick on the C2H2 down here. I kind of said like you take your final Lewis structure and draw kind of like a little Venn circle around it. So let's go ahead and we'll pick red, I guess. And for this left carbon, I'm going to go ahead and draw a circle around everything around that carbon. So the magic number is 8. So 2, 4, 6, 8. We got it. And I could do it, it's very symmetrical. I could do it for the right carbon. We have 2, 4, 6, 8. But see how those 6 electrons are shared between those 2 carbon atoms? Okay. I'm sure there should be a t-shirt out there that says, we should be more like covalent bonds. So a covalent bond on a Lewis structure is a dash. Now, there are 2 types of covalent bonds that I need to talk about. If you want at the top, sometimes I call this the first to arrive. And it's implied when I say primary, first to arrive. First to arrive at the scene. It is primary. Now, it's got the kind of the circle with a tail. Okay, that is the Greek letter sigma, a lowercase sigma. So we call them sigma bonds. They're primary bonds. They're first to arrive. And so like on that first structure, that C2H6 with all just those single dashes, all of those were sigma bonds. And actually, I have C2H6. So the black balls are carbons, and the white balls are hydrogens. And the gray things are sigma bonds. So I'm going to go this way. C2H6. So one of the things, actually this is the last point about sigma bonds, is the gray things we say are kind of lined up with the center of the atoms, the nuclei of the carbon atoms and the nuclei of the carbon and hydrogen atoms. So they're oriented in a straight line. That's our primary sigma bond. Okay. So, my grandmother, bless her heart, passed away years ago, but one of the things I remember about her is when we would go out to eat, she would always ask for dessert first. She'd be polite about it. She's like, can I see your pie menu? We'd go to Perkins.
My mom's the same way. She does that. She always eats her dessert first.
And see, somebody say, why not? I think, we should. So, but, of course, you probably heard of the Greek letter pi. Okay, there's the Greek letter pi. That's why I think a dessert is pi. So the pi bond is the second to arrive. And it's a secondary bond. second to arrive. Now, do we always have dessert? No. Some people, like my brother, doesn't like desserts. I'm like, are you serious? Can I have yours? So only if you have the first type of bond, the sigma bond, do you have a possibility of having the secondary bond. So the previous things we looked at, like the C2H4 and the C2H2, we drew a double and a triple bond respectively between those two carbon atoms. So for that double, I'll just kind of do it up here again. So for that carbon, double bond carbon, I'll just kind of draw the heart of it. Okay, I kind of think of the first one to arrive as sigma, and the second one to arrive as the pi bond. Now, do I know which is which? No. Well, sort of. I'm going to show you here in a minute. So carbon, triple bond carbon, like we've been saying, the first to arrive is sigma, and then we've got actually 2 pi bonds. Okay. So one more thing to talk about with regard to the pi bonds is where, if there's 2 electrons, if there's a pair of electrons creating this between these 2 carbon atoms, then where do those electrons go? And here's your answer. They basically kind of schmooze around outside the primary bond. The pair of electrons, and I have an example up here. This actually is C2H4. C2H4. So here you see the grays are the sigma bonds. Now you see a pink purple, okay? And this is hard for me to wrap my mind around. Actually, the pink purple represents 1 pi bond orbital where a pair of electrons are. And it's kind of like a sandwich sort of thing. They are actually located above and below. They're outside of there. Okay. So there's that one, but it gets even better because the last structure I have is this one. Okay, so this is C2H2. And of course, the gray are the sigma bonds, first to arrive, primary bonds, pair of electrons connecting all those atoms. And we said in that case you have 2 pi bonds. Okay, so here we go. 1 pi bond, second pi bond. So I actually have 4 electrons that are kind of buzzing outside, creating those 2 secondary bonds. That's C2H. So you probably already get a sense, and we're talking more about this, how kind of there is a rhyme and reason to kind of how the shape of a molecule ends up. That one that Becky's got, the C2H4, it actually, if you were to take away the purple and the pink, it's what we call planar. It lies in a plane. This guy right here, the C2H2, it's like a hot dog. It's linear. So that's planar, and that's actually linear. The other one that went around, you couldn't stick that in a plane. And it's definitely not linear. So the bonding is a player in the shape of the molecule. I will say one more thing. Sometimes I forget to say this, but I'm going to go ahead and rotate this thing. This guy, it totally rotates. Okay? The other 2, nope. All sorts of things. So we actually even talked about this morning, if you want to know the valence electrons in an element and you have a periodic table handy, what do? You look at the group number to tell you the valence electrons. Well, not to confuse you, but there is this other aspect of atoms when they are bonding to other atoms bonding to their fellow atoms, and that is what we call the expected valence of an atom. The expected valence of an atom is not the same thing as valence electrons, but they are related. Sometimes I call this kind of the reaching out. Expected valence is the number of times it will reach out. Number of times it reaches out. It being an atom. So number of times atom reaches out. That Kind of think of it as like an octopus. And by reaching out, it's going to reach out, use it with primary bonds and secondary bonds. Oh, and then, but this only works if we're dealing with a neutral molecule. So, the little formula, it's a little subtraction. Okay, basically, if you want to know the expected valence for any atom, again, you have to have a periodic table handy. But it's a little subtraction. You take the group number, okay, and you subtract it from 8. So 8 minus the group number. And that gives you the expected valence. All right. Well, we said hydrogen only wants 2 electrons and boron wants 6. So they don't follow the octet rule. And for that reason, hydrogen will only reach out once. Hydrogen will only reach out once. So on your Lewis structure, you should see it only extending once. And sigma's first to arrive, so it actually is going to be 1 sigma bond for hydrogen. Boron will extend itself 3 times. I don't do much with boron in this class, but so here we go. If I add a column here for the group number, carbon is group number 4, nitrogen, phosphorus, group number 5, oxygen and sulfur 6, the halogens 7. And then I could add another column, and I could say 8 minus group number, just to emphasize what this slide is. So 8 minus 4 is 4. 8 minus 5 is 3. 8 minus 6 is 2. Okay, 8 minus 7 is 1. So these are all the expected valences if that atom is in a neutral molecule. So this is a number of sigma and pi bonds. Okay. All right. So these probably look familiar. Remember when we talked about electron dot structures? Where here we have the symbol of the element represents the nucleus and the non-valence electrons. And then these little dots are valence electrons. So if we look at this, it kind of tells you a little bit how many times it will reach out. So we said the expected valence of a carbon atom is 4. If you go ahead and, it's kind of like parking a car. I can park 4 cars here with these electrons that don't have a car already in there. Nitrogen has 8 valence electrons, so I can park 3, nitrogen has 5 valence electrons, So I have room to park 3. Oxygen has 6 valence electrons, I have room to park 2. The halogens have 7 valence electrons, I have room to park 1. And there is no room at the end for nitrogen, for the rare gases, for neon. All right. So Lewis structures like that water that we did earlier today. I already talked about the pot of valence electrons brought by the 2 hydrogens and the oxygen. So the checks we'll be doing on Thursday is coming up with a pot of electrons that we should be on our structure and then making sure our structure has it. So that's going to be actually step 1 is to come up with the pot of valence electrons. Step 1. And we're not going to go through the steps today. I think we'll get to them on Wednesday, though. So it's kind of like our water molecule. Again, when we did the Lewis structure of our water molecule down here in italics, it says, so we had 8 electrons to do something with. And we knew we wanted to give oxygen 8 and the hydrogen's just 2. And anytime we put something on our Lewis structure, if you put a dash, okay, anytime you put a dash, it's 2 electrons. A double dash would be 4, and a triple dash would be 6. And those dots like we had on the water molecule, okay, these actually, for us anyway, will always go in pairs. And they will help give shape to the molecule, so don't disregard the dots. And in the case of oxygen, it helps give it a complete octet. But those are electron pairs, our lone pair electron pairs are called, they're non-bonding, they don't bond. All right. So it's, when I drew this H2O molecule up here, the letter oxygen represented the nucleus of the oxygen atom and the non-valence electrons, kind of like we did before. Would just be elements. And I kind of feel like we're just kind of rehashing something we already talked about a little bit ago. If you see a single dash, that's it. Now we know it's a sigma, a primary bond, 2 electrons. If you see 2 dashes, that's a double bond, 1 sigma, 1 pi, that's 4 electrons. If you see 3 dashes, that's a triple bond, 1 sigma and 2 pi's, 6 electrons. Lone pair, dots. What else we got? And then that last item up there, remember we talked about when you have the electron dot structures for the elements, there's no uniqueness about kind of the north, south, or east, west, top, bottom, left, right. So when we draw Lewis structures, obviously we're using paper and pencil, and it's two-dimensional. But if you know what you're doing, and we'll talk a little bit about this tomorrow and in Thursday's lab, you can actually kind of infer 3 dimensions from your 2-dimensional drawing. So let's look at a few. This is ammonia. And just to kind of get the ball rolling, let's come up with a pot of valence electrons for the formula NH3, and let's check to see if it's on the structure. So the element nitrogen, there's 1 nitrogen atom. It's a 5A element, so it brings 5 valence electrons. For hydrogen, there are 3 hydrogen atoms. They each bring 1 electron. So wow, looks like we got 8. Our pot of valence electrons is 8 again. So all I mean then is if we go over to the structure, and here's a sigma bond, 2 electrons, 2 electrons, 2 electrons, and then of course we have those lone pair electrons, 2 electrons. So it looks like 8 to me. And then maybe not so obviously. Another check is if we draw a circle around the nitrogen atom, does it have 8 electrons? Yep. Happy, happy, happy. Joy, joy, joy. Let's do a similar thing for H2CO. So we have, with regard to the element hydrogen, there are 2 hydrogens. Valence electrons is 1 valence electron. With regard to carbon, there's 1 carbon atom. It's a 6A element, so 6 valence electrons. And then with regard to oxygen, there's 1 oxygen atom. Wait, I was wrong, wasn't I? I know you guys would have. Carbon, sorry. It's 4A, so there's 4 valence electrons. Yep. Because then it threw me off. Oxygen is 6A. There's 6 valence electrons. Cool. So if we add them up, it's looking like 12. My pot of valence electrons, so let's take a quick look. I got 2, 4, 6, 8, 10, 12. Looking good. Let's just draw a circle around the oxygen and see if we got an octet there. So here goes the oxygen. 2, 4, 6, 8. I'm liking it. We could draw a circle around the carbon. 2, 4, 6, 8. I'm liking it. So before we leave this, let's do one more thing, the how many times it's going to reach out thing. So the expected valence. So for carbon, I'll put carbon and then valence. And remember, valence is 8 minus the group number. So 8 minus carbon's group number is 4, we decided. Okay. So the expected valence, and that, by the way, is the number of times it's going to reach out. So reaching out for sigma and pi bonds. All right, so find carbon. So reaching out, I got it reaching out 1 for a sigma bond, another sigma bond, a sigma bond here, and a pi bond here. So it is reaching out 4 times. So that's how that works. Let's pick on oxygen. So for oxygen, we're going to take 8 minus its group number. Its group number is 6A, so 8 minus 6 is 2. So we expect oxygen to reach out sigma and pi bonds twice. So over here, we got 1 sigma bond, 1 pi bond. So it is reaching out twice. So that's how that works. And last but not least, so we can draw Lewis structures of molecules. Okay, the NH3 was a molecule, the C2H6 was a molecule, the H2CO was a molecule. We can also draw Lewis structures of polyatomic ions. One of the polyatomic ion, those halogens are just so annoying with their polyatomic ions. They are. They can go down to just 1 oxygen, and then they go with the hypoite. So we have hypochlorite here. You can draw Lewis structures of them too. And the reason is because those atoms are actually connected with covalent bonds. So let's do a pot of valence electrons right quick. Well, it's going to seem kind of strange. So for chlorine, there's 1 chlorine atom. It's a 7A, so it's got 7 valence electrons. For oxygen, there's 1 oxygen atom. It's a 6A. Okay. Now, one more thing. This is our pot of valence electrons. We need to take into account that actually it has picked up 1 extra electron. And so what I usually do is simply say for the charge, it's free. No. For the charge, it's got 1 electron. 1 extra electron. Now, if it was -2, it would have 2 extra electrons. So it's, to me, looking like 7 plus 6 plus 1. I got 14. All right, so let's see if we have 14 electrons over here. 2, 4, 6, 8, 10, 12, 14. So that checks from our pot to that we think we should have from the formula to the structure. It's great. Now let's look for our octet. Okay, let's draw a circle around the chlorine. And when I draw a circle around the chlorine, it looks like it's got 8 electrons. And I can draw a circle around the oxygen, and it looks like it has 8 electrons too. Let's do one more check, the check for valence. Wow. So we said valence is 8 minus the group number. For chlorine, if we take 8 minus group number 7, okay, we expect it to reach out once. That's the valence. It's doing that. For oxygen, it's 8 minus the group number, which is oxygen at 6, so we expect it to reach out twice. And here's the deal. It's only reaching out once. But remember the slide where I said this expected valence works only for neutral molecules. So actually, the expected valence is not applicable. Na for ions. So now I know there's an assignment slide next, right? And actually, I don't know how this got kind of topsy-turvy. This, we'll get to this assignment slide tomorrow. So this is slide, since it's gonna be a Wednesday lecture that we get to the assignment slide, these won't be due until Friday. Do you know what I'm saying?
Yeah.
Okay, so I'm gonna show this slide at the end of part 5.
Show it how.
Yeah, so if you wanna put end of part 5, you can, because that'll be, we're gonna get to that tomorrow. And we're not gonna go on part 5. Any questions? That's a lot. All the stuff we talked about today is great, and then we're gonna piggyback on that.
Do you think
In
we'll be
Wednesday's
able
lecture.
to do it today by just learning what we just learned, the homework, or do you want us to
Probably.
wait? Okay.
There might be some subtleties. Yeah, there's some subtleties, and yeah, it's just kind of misplaced. But after tomorrow, I think you should be able to.
Okay.
Yeah. And definitely after Thursday. Thursday, we're just taking
Yeah,
a hit, yeah. But Thursday's another lab not to miss.